Hi everybody, welcome to my first torsional bar video. So the definition of a torsional bar is this. Alright, just that simple. A bar that is being twisted. Alright, and I want to say straight off the bat that the mathematics and the way that we analyze torsional bars is nearly identical to the way that we analyze axial bars. So if you're comfortable with axial bars, you'll be comfortable with torsional bars as long as you realize that there's very striking similarities between the two. We just pretty well use different symbols and different units. So just like axial bars, there's lots of types of torsional bars. Alright, so here's our basic torsional bar, something stuck in a wall. And when we apply a torque, or we twist it, we use an arrow, just like we did when we had a force, but in this case, we make it a double-headed arrow like that. It indicates a torque. And the direction of the torque is always, you take your thumb, in this case the torque is pointing that way, and your finger is curling this way, so this whole thing is twisting that way. Alright, and there's of course lots of other examples. I'll sketch them out for you. So in this case, torsional bar with different torques being applied at different discrete points. You could imagine a bar that has some sort of varying area. You can imagine a bar that has a constant area and has some sort of applied torque throughout it. So this twisty arrow that you see, it's twisting from here and going in. So what's the direction of this torque? Take our right hand, well, it's twisting this way, so this torque is actually going to be pointing in like that if we would replace it by some torque like this. Alright, and of course we can imagine a torsional bar that's a composite made out of two or more materials. Alright, so you can pretty well imagine any combination of these. Alright, notice again that we had axial bars that had all of these same sort of conditions. Now we're just applying torques to them instead of forces. So there's lots and lots of practical uses of torsional bars or bars that are being twisted in the real world. Alright, the first one that I can think of that's the most prevalent in engineering are generators. Alright, and shafts in generators that spin particularly. Alright, there's lots of kinds of shafts and different kinds of generators I can think of. Alright, lots of different generators. You can have generators for dams, ones that power your house when the power goes out. You can even think of ones that you use just on job sites to get electricity for your equipment. Alright, so lots of generators. They produce electricity by spinning a bar inside a magnetic coil. And then by electromagnetic induction, you get electricity. So that's one of the major applications of torsional bars. And of course we're going to have things like drill bits, right? Alright, so basically, anything that spins and used to drill a hole or anything like that. Alright, drill bits. All right, oil drilling. When you drill for oil, you have a big thing that spin. Screwdrivers. Right, it's pretty well universal. You can also think of like buildings. Buildings and bridges, right? How are they torsional bars? Well, they're not bars per se, but if you have wind, they do twist in the wind, and you can analyze them using some of the principles that we will develop to analyze, torsional bars. And of course, you can imagine like different vehicles. You have axles, all right? That's basically connects a tire to a tire and makes sure that they both spin. You can find these on. Alright, and the list goes on. And I'm sure there's more examples of torsional bars, but these are the ones that I could think of. And of course I have some nice pictures for you. So going back to the dams, I have here a picture of the Hoover Dam rotor. So basically it's this big column here you see. So at some point the water will be rushing in, spinning this way, and there will be some sort of propeller on here, I guess you could call it. And that will spin this shaft, and that will spin inside all these rusty looking things. That's the coils that will make electricity. So this big thing here, that's a huge example of a torsional bar. And later on, we're actually going to specifically look at examples of torsional bars that are used in power production. We'll be calculating things like, what does this diameter have to be if we want to produce a certain amount of power. Alright, so this is probably the most important use of torsional bars in the real world. And I have another picture here, a tunnel boring machine. So this big contraption is used to bore a tunnel, right? So basically what happens is this whole head here rotates, excavates the soil, and then moves it along, perhaps over some conveyor belt out of the end of the tunnel. So you could analyze, this piece of equipment here using torsional bar methods because this thing is spinning. Alright, and I've got a few more practical examples that you probably use, maybe once or twice a week or in a month. Got a drill bit here, drilling into wood. Alright, so we can figure out, optimum like efficiencies and that type of thing of a drill bit. Because it turns out in torsion, when you're like twisting something, most of the torsion is picked up by the outside of the drill bit. So you can basically hollow out the inside and have that drill bit do the same job. So we're going to do some calculations that, look at that, and then of course the hollow drill bit is a lot more efficient, uses less material. And of course a trusty old screwdriver. Alright, you spin on that thing, it's going to act as a torsional bar. You can also think of like, some sort of lug wrench you use to take the bolts off your tire. Alright, and here the last picture, maybe not quite as clear, but this is an axle to a semi-truck. You can see the axle right beneath here. It connects the tires. So this is also a torsional bar, and we can analyze it using like, the power, right? If the truck has 400 horsepower, what should the diameter of the axle be so that when it takes off it doesn't, just shear off. Alright, and of course there's lots more torsional bars, and I encourage you to think about torsional bars in your everyday life and think about how you can apply the principles you used in this course to those everyday examples. So let's move along into developing some of the equations we're going to need. And I'm not going to do an explicit derivation of the equation, I'm just going to do a comparison to axial bars. So in axial bars, this series of equations you should know. And alright, so you should recognize this equation. This is stress, alright, and then you can rearrange this to delta equals to NL over AE. And here you have the differential form of that equation. So this is pretty much an equation that sums up all the equations in axial bar world. So in torsional bar world, we have an equation that's like pretty well identical to this in terms of similarity. So in torsional bar world, instead of a modulus elasticity, instead of Young's modulus, we have a shear modulus. We'll call that G. Alright, now d delta here, that's an elongation. In torsional bar world, we have twist, so it's going to be an angle. So we can say d phi, and the dx here is still the same. Alright, and let's just go right through here. This is essentially the same, right? E is g, delta is phi, and the length of the bar, it's exactly the same. Now this piece here is going to be slightly different, but I'll explain it. So, axial bar world, we had normal force. Torsional bar world, we have a torque. That's T. And here we have area. Now we're not going to have area in the torsional bar world. We're going to have another quantity, the polar moment of inertia. I'm going to call that J. Alright, you might call it something else like I sub P or something. I call it J. And I'm going to explain to you what J is in just a few seconds here. So it's basically like force over area in the torque world is equal to, well, this is sigma. So that's stress. Alright, but here we're going to be talking about shear stress, tau. And this would be like identical similarity, but in fact we have to divide it by the radius in this case, because in a torsional bar, the further you go away, alright, these quantities are going to be changing. Alright, so this is the the basic set of equations that you were going to need to use in this case. So torque, second moment of polar moment of inertia, shear stress, radius, shear modulus, angle of twist, length. And then of course that's just the differential form. So all of these we've seen before, and I think in one of my very first videos I developed the relationship between G and phi and those type of things. So you probably have some basic understanding what G is. Well, let's go into what J. Alright, so it's basically the second Alright, now in the one of the next videos I go through and explain, moment of inertia, moment of area, all these first, second moments, and areas and torques and all these things. I go into an explanation of this, but in this video I'm going to only talk about J. So the second moment of inertia is defined, as you might know, as the integral over an area of some distance, we'll call it r, squared dA. Alright, so that's the formula for the second moment of area, or the moment of inertia. Alright, and we're going to call it J. Now, in a torsional bar, it's always round, and it has a total radius, big R. So if we're going to go and solve this integral, we need to find what dA is. So you can imagine a small section here, dA. Alright, let's just blow that piece up. Okay, so if this is an very small area, an infinitesimally small area dA, that means each of the side length must have these differential forms as well. So this small distance in the radial direction, we'll call that dr, right, because it's a small distance in the radial direction. And this bit here has to do with this small angle of change, d theta, and we know that for any radial distance here, this distance theta, let's call this s, and this is r. So we can say theta is s by r, or the s is equal to theta r. In our case, this is a small angle d theta, so this distance is d theta r, or r d theta. Alright, so we can say, alright, this is basically some calculus. We can plug this back in here. Alright, now why did I get two integrals all of a sudden? Well, that's because we have two variables, r and theta. So integrating r from when r equals 0 out to big R, and theta, well, that's just, all the way around. So that's 0 to 2 pi. Alright, so you can integrate this dr piece first. It becomes r cubed by 3. Alright, and we can evaluate from r equals 0 to r. I'm just going to get big R cubed. Oh, sorry. This is R to the 3 already, so it's R to the 4 over 4. Let me just completely rewrite that. And of course, we still have the integral from 0 to 2 pi d theta. And since it doesn't depend on theta, it's just times 2 pi. So in the end of the day, we get pi by 2 radius to the 4th. So that's our final expression for the polar moment of inertia. Right, and this is called polar because we're taking it about this polar axis. Other moments of inertia, you might do like a square or something, and you won't call it the polar moment of inertia. So lots of times, instead of R, you can use D. All right, and we know that so if we plug this into here, and we take it all outside, we can all say that it equals to pi by 32 d to the 4. Right, because you just take 2 to the power of 4 times 2, that's 32. So these are the two most common equations, and I'll use them interchangeably. Alright, so hope you enjoyed my first little bit of intro to torsional bars, and I'll see you in my next bunch of torsional bar videos where I talk about everything to do with torsional bars.